So in this video, I want to do the test review for chapter 15. The video is going to cover all the problems. If you want to jump to a particular problem to see how I work it, then you can use the timestamps that I have in the description of the video. Okay, so for this first one here, this is really going to wind up as primarily a plug and chug type of problem. Notice here that you are given information about the initial pressure as well as the equilibrium partial pressure for the reactant here. I'm going to set up an ICE table so you can see how everything changes during this reaction and where the data goes, etc. Okay, so my initial data, I have 1.66 atmosphere. And then the equilibrium partial pressure, now that's going to go in the table down here. And when you have a setup like this, where you're given initial and final states, well, you can actually fill out the entire ICE table and plug and chug into the KP expression, okay, which we'll do in just a second. So, you know, what's the change line here? Well, it's whatever difference it takes to get to, you know, from the 1.66 down to the 0.967 value. And if you subtract the two, you find that difference is 0.693 atmosphere. So that establishes the change for the entire, or the value for the change line for all of the compounds in the equation. Now, since the initial concentration of the reactant is decreasing, then that also establishes our sign notation from one side of the table from the next, meaning that, right, if the reactant is decreasing by a certain amount, then that's going to dictate how much the other side is increasing. It's not written in there, but I'll go back in just a second and point out something we kind of already knew, right? There's zero concentration or partial pressure of the two products. Nothing is stated in the description of the reaction or the description of the problem, so we can assume that it's down at zero. So, you know, kind of if you just sort of do the math here, right? 0 plus 0.693, well, that tells us how much the partial pressures are for the two products. And now we're really ready to plug and chug into the KP expression. Now, before I do that, I do just want to point out one little thing about this particular equilibrium reaction. You know, since we're at a 1-to-1-to-1 ratio here, well, that's what makes, and I'm being a little bit redundant here. Remember, the molar coefficients down or up in the balanced equation dictates the, let's say, multiplier that you see on the change line. Now, again, since it's 1-to-1-to-1 here, that 0.693 value, just it's the same quantity all the way across. It's just a sign that changes. But, you know, if there was a 2 here, then there would be a 2 there, and that would affect the concentration, or I should say the partial pressure of that particular product in the expression. Okay, I have all my values I need. I can then go in and I can calculate my KP at equilibrium for this particular temperature, and let's just see what that looks like. And remember, I'll just go through, it's all gas phase reaction. It's all 1-to-1-to-1, so nothing is raised to any special power. Okay, everything's raised to the 1 power. So it's going to be the product of the product, so up top, and then the only reactant there down at the bottom. We can plug in our values from our ICE table. And if I do the math here, it comes in at the 497. So it's just under 1. Right? It's telling us that, I mean, in some ways, this thing is fairly close at being equal on both sides. It really doesn't proceed very far forward at all. Certainly, the products certainly are not favored, right, in this particular example. Now, for problem number 2, what we see is really just setting up a couple of equilibrium expressions, or what it's a law of mass action equation for these examples here. Now, the reason why I have this in the review sheet here is just to remind us how we handle pure phases versus aqueous and versus gas. Okay, so both of these are heterogeneous equilibria. Oh, and I guess technically I should have had double-headed arrows here, sorry. But the liquid and the solid are going to be omitted from the expression. So it just simplifies the expression quite a bit. Now, since we are dealing with aqueous, that usually, well, it's always a molar expression. So I'm just going to go ahead and change. Instead of KEQ, I'm just going to add the C for concentration. The form of the expression is the same, right? We're going to have the products over reactants. There's our products. Notice we got some big coefficients here, so they are going to get worked into the mathematical formula. So we got phosphoric, and since it's 4 on the molar coefficient, then it's going to be raised to the 4 in the formula. Hydrochloric acid is now going to be raised to the 10. Of the 10th power, since it's 10 on the molar coefficients. And then the only reactant is the hypochlorous acid there, and that's going to be raised to the 10th power as well because of the molar coefficients there. And that's it. There's nothing else to do with it. B, same kind of deal. Pure substances are omitted. Now, since it's gas here, I could do Kc for concentration, but typically you see Kp. If this problem was given, or if this equation was given in a problem, usually you would be given atmosphere value for the gases. But if you were given, the number of moles in a certain number of liters, right, you could convert that to a molarity. So you do see that occasionally. So just a heads up for you. But traditionally, we're dealing with atmosphere. So we are going to then use just a partial pressure notation, kind of like what we did in the first problem. And the same deal, we only have one product. It has a molar coefficient of 2, so it's going to be raised to the 2nd power. And we only have one reactant. So there's only one denominator there, and it's going to be raised to the 3rd power because of that molar coefficient. And that's it. In the grand scheme of things, these expressions, when you first get a hold of them, might be a little bit weird, but with a little practice, they're not too bad if you're just trying to develop the expression for that equilibrium. Now, for the next problem, it's a little bit more work. This is an example. I guess there's a couple things that this problem is trying to get across. First thing is this idea of, it's kind of like, I've mentioned this in class, kind of like Hess's law from Gen Chem 1, where you're given a couple of expressions there, and you want to rearrange those expressions so that you get this new equation, and then you're going to manipulate the equilibrium constants for those that are given to then calculate the expression for the problem there. Now, just to make this a little bit easier for us, I'm going to go ahead and change this to the Kc expression. That saves us a little step. If we wanted to calculate Kp, we'd first calculate Kc, and then we would use that equation to convert between Kc and Kp that we talked about in class. But I don't want to do that here. I want to focus on just this manipulation of the formulas first. Now, the main thing that you want to do is go in and start trying to find your reactants and products in your target expression. For example, notice that nitrogen and oxygen are showing up on the product side of that second expression, and bromine is showing up on the reactant side of that first expression. Well, what that suggests to me is that I'm probably going to have to flip. Actually, I know I'm going to have to flip that second one, right? I want to get these things on the other side so that they match up with my target expression. And then the other thing that I'm noticing here is that the only product in my target expression does show up as a product in that second one, or that first one. So I'm not going to be flipping that first one. It's fine. So let's just go ahead and flip that second one there and see how we manipulate. I'm going to drop the phases just for convenience for a moment. And it's NO2. Now this new Kc for this value is if you flip an expression here, you're going to invert the Kc from the original equation. So just to be clear of the math that I'm doing here, it's 1 divided by that original Kc, and that gives me a very small number, 4.8 times 10 to the minus 31. Now, since I have now used that, I'm going to mark that out so I don't go back and mess with it. And then the other little thing that you always want to check on is that if there's any what I'm going to call intermediates, something that, for example, shows up in the two expressions, but it's not actually in the original or the reaction we're going toward. In this case, it's the nitrogen monoxide gas. And, well, notice that 2 moles of each of those, right, 2 moles here, 2 moles there, they're on opposite sides of the equilibrium expression, meaning that you have, you have one on the reactant side up here, you have one on the product side down there. It actually allows you to cancel that particular chemical species out of the given equilibria, and that is consistent with the fact that there's no NO in that target equation. And now, if you go into this problem, and then you add up the equations that you have, this guy and that guy, then what you see is, and I'm going to just put a little divider here, a little divider there. Right, we got bromine, we got nitrogen, we have oxygen. Let's just put those in the order that is it's the same as this up here, just for convenience. It really doesn't matter. And notice it has the same molar coefficients. It's the only thing that's present on the reactant side. That's good. That's what we want. And then here we have one of the NOBR. I'm sorry, 2 NOBRs, 2 NOBRs up here. And so that's the only thing that's being carried forward. And that's it. You're done. The fact that we've added up these two equations so that it equals this target equation tells us that we've set this thing up correctly. And then the last step here is, how do we go and handle these values to come up with this new Kc for this reaction? Well, once we have the Kc's in place, we're really just going to multiply them together. So it's 2.0 multiplied by the 4.8 times 10 to the minus 31. And if I do the math here, I do get that 9.5 times 10 to the minus 31. Just a little commentary about the smallness of that value. Basically, it's saying that this reaction, this equilibrium, is not favored at all going in the forward direction. The primary reason for that, just sort of guessing, I've never done this reaction or anything, is nitrogen's very stable. It just doesn't tend to react, especially, so this is at room temperature. So even though you have something extremely aggressive like bromine, oxygen is reasonably aggressive. It's just not enough to break the triple bond of that nitrogen. So just a little commentary about, how a chemist looks at an equation like that and how they interpret numbers like that. Now, in this particular problem, we are going to calculate Q, right? The Q expression looks just like the Kc expression. It's just that when you go and plug and chug for Q, it's the initial values, not the equilibrium state. And so the initial values are given here for this problem. And like I said, Q has the same form as the K's, the equilibrium constants. So ammonia is going to be raised to the second power. It's the only product. We have nitrogen and hydrogen as the two reactants. Hydrogen is going to be raised to the third power. And now you're just going to, plug these values into that expression and just make sure you get everything lined up properly. I'm going to drop the units just for convenience because they're going to be dropped anyway in a minute. And hydrogen is going to be cubed. If I evaluate that expression, I get a number, and it's at 1.3 times 10 to the minus 3. Okay, so that would be the value initially. And notice in this problem, there it is, it actually gives you the Kp, equilibrium expression for this particular temperature. And so what we have to notice is that, it's not that, what we have to notice is that the exponent here, 10 to the minus 5, is much smaller than the 10 to the minus 3 there that we get for Q. So what we say is Q is greater than the Kp. Well, if Q is greater than Kp, then essentially what it's telling us is there's too much product in this expression, right? If this value is greater than what it should be, if you will, then if you just think it simply as a mathematical kind of a relationship, it just means the denominator is larger than it should be. So if this is large, then to reach equilibrium, it's going to shift back toward the reactant. So this one is going to form reactants at that particular state at that particular temperature. If that was reversed, then that means products would form. And then one particular special case to know, if Q and K are equal to each other, then what that means is that the reaction is already at equilibrium. Okay, so there'd be no change. Our last problem is dealing with Le Châtelier's principle. Right, this is kind of a classic kind of setup. There's some kind of stresses being described here. Okay. And it's on this particular reaction. And the easiest ones, and let's do those first, that's where you see like an increase in the concentration or a decrease in the concentration of the different reactants or products there. And let's just take them one at a time. And so the first one is that, and we'll just sort of scribble in right here for A. Ammonia is being increased. There's ammonia there. Right, so that means you're jacking up the concentration of this ammonia. And what Le Châtelier's principle says is that if that kind of change is going to result in it going away from that increase in the concentration. So in this case, it's going to shift toward the right, or you could say it shifts toward the products. The next one, I'm increasing water. There's water, okay? If I'm increasing water, then it's going to go back in the opposite direction. B, it's going to shift back to the left. Or you could also say, shifts toward the reactants. And then finally, the oxygen changes. We're going to decrease the oxygen. So imagine removing it in that scenario. And, you could think these equilibrium reactions are kind of like a seesaw. If this one goes down, it's going to go toward that direction. And so in this one, it's going to shift back toward the reactants as well. Sort of the next easiest one that I'm looking at here, adding a catalyst. Well, catalyst, there's no effect. The only thing the catalyst is going to do is it speeds up the reaction. So the reaction reaches equilibrium more quickly. But the actual, concentrations of reactants and products are going to be the same. Okay, so the catalyst does not affect the equilibrium position at all. The next one I want to do is to deal with temperature. I'm saving the most difficult one for last, which is that decrease in volume. Okay, so to address F there, increase in temperature, well, let's look at the enthalpy value. Okay, so we have a negative enthalpy value. Right? Enthalpy is a state function of that equation. It's like almost like a physical parameter describing the reaction. The increase in temperature here is something that humans are doing in the lab, that you're doing in the lab. So the way to interpret this is the enthalpy says, okay, it's a negative value. That means it's an exothermic reaction. That means heat is, think of it as a product now. Okay, so heat is a product that's some kind of a fundamental property of this reaction. You're changing this. Well, if I increase temperature, what that means is I'm adding heat now to the flask or whatever this thing is contained in. It is essentially as if I am increasing the product for this particular reaction. Okay, right? Because heat is a product on this thing since it's exothermic. And just like in all the other examples, I should say the ABC examples, if I'm increasing one side, then what that means is it shifts back toward the opposite side. So in this case, it's going to shift left as well. If I was to remove heat, it would shift in the opposite direction. If that was positive, that means that it would be an endothermic reaction, okay, and then heat would be over there. And then you would base your shift in the equilibrium on that information. Okay, the last one I want to do, the more difficult one, is D. Let's talk about D. Okay, so in this case, the volume of the container is decreased. Okay, so let's sort of think about what that means. And in class, what I did is I tried to draw a kind of a system here with let's say a piston going down there, and then there's gas particles sitting in there. And if I'm decreasing the, and it's not drawn to size anyway because I'm not a very good drawer. There we go. And there we go. I decrease the gas particles, the space that the gas particles can float around in. Well, I mean, what's the net effect? The really, they won't. There's less volume to sort of adjust back to equilibrium. It's wanting to go to fewer moles of gas. So in class, I talked about the volume and the number of moles of the gas are proportional to each other. They're going to change together. Volume and decrease, the number of moles are going to decrease. So what do I mean by that? Well, the number of moles here, if you look here, we're dealing with all gas phase reactants and products. So let me just kind of rewrite this down here, and I'm looking at the molar coefficients. So on the total, on the reactant side, I have 9 moles of gas. And on this side, I have 10 moles of gas. So if I'm trying to decrease the number of gas particles, there's only one direction I can go in this equilibrium. I want to go to the lower number. So the answer for D is that it shifts back to to the left, trying to decrease the number of gas particles there because you've given the molecules just less space to move around in. Okay, I think that's good for this review. And again, if you want to back up to a particular problem, there are timestamps down in the description of the video, so you can jump around to review whichever problem you want to take a look at. Okay,